Okay, so this is Unit 2, Part 1. Yeah, they divided into 2, and we're going to learn the statistical application of predictive maintenance management. So the first thing you need to know is reliability. So reliability engineering is a big thing in industrial technology. So industrial engineering technology, same thing. And you can also get certification for that. So what's reliability? It is the ability of your system. Here's a cartoon here. That's your system. That's all connected. Okay? So reliability is the ability of the system. Ability meaning like what that system can do to perform its intended function. Okay, what it's using during its expected life period. We all have life, and none of them is ever functioning thing. So always have expected life for each of the components of the entire system itself. So we do maintenance and to keep the system working, and that system will be only during the system life. The system beyond its predicted life. Also, each component cannot go beyond its predicted life. So that life is important. Dealing with the system life, you're dealing with life for each component in that system. Okay? Again, reliability is the ability of the system to perform its intended function. And you want to keep that ability going to the end of that life. Okay? So we will maintain. Okay. So system is a logical collection of components in series or parallel arrangements working to perform a function. You already know system, they have components. Okay, these components are how do I say? So these components are connected to each other, okay? Processes and operations. And they're all linked. They're physically linked. And doing a particular function for each component within the system. So you will see that they're all arranged either in series, okay, or parallel. So meaning like that. Just draw this diagram like this. Okay. This means series going one after another. Parallel is kind of like a stack. Okay, the system's a step, and they're all connected. Okay. So this is just a different arrangement that you can be able to see. Parallel system, series. And again, point for these arrangements is logic. Okay, so don't get this word right here, logical collection. Okay, logical collection. And I threw a question last semester, and I give them one illogical collection to test if the student can be able to understand, recognize, okay, how then this word logical collection. I think come up with it out of 20 something students. So anyway, 27 students. So don't just read it as system and collection. No, system is a logical collection of, so those components are arranged in a particular way to run the system. You can't just deny everything. No. They are in series, they're in parallel, they are in a systematic arrangement for that system to run. Okay, and they got to be logical, meaning like circuits, okay, got to be in the right way. Positive terminals and negative terminals, they won't shock the system and destroy the game illogical management. Okay, engineering, technology, maintenance, management, checking that foul play can have a temper the system to destroy the system. It's a possibility that any human can do. They go to bad or the direction, and even if we're maintaining the system, operators are the system, so you're also being monitored in the system, okay, in order to prevent illogical arrangement. One nonsense arrangement can take down the entire system. So therefore, this little word right here is the most important there. Okay, terrorists can destroy the system. Hackers destroy the system by doing that. Okay, illogical code, illogical circuit systems to destroy the system. So, and logical got to be the logical action of components. You don't need weapons to destroy the system. All you need is an expert, so they want to go and attack the system. But if they want to destroy, they can do it. So one simple, illogical arrangement. So make sure not to think this word lightly. Okay, that's enough of that. So we have series systems and we have parallel system. We can arrange the components in series. We can arrange the components of the system parallel, and in combination of that system, you will see many series and many parallels, okay, all together. Many people to check out. Again, it's got to be logical. Reliability, system reliability. We have two different arrangements of the system. Take a look at the series. Looks like this in diagram. These components, they are arranged one after another. Okay, and we call that components of a system are arranged in series. The system reliability is the product of the reliability of each individual. Okay, system is made of components. Therefore, the system reliability is the reliability of each individual. Okay, so component 1, you have reliability that component 1. Component 2, reliability of that 2. And 3, of the reliability 3. System reliability depends on this. Okay, parallel looks like that. So when components of the system are arranged in parallel like this, system reliability. Okay, the same thing. System reliability. We have component 1, we have component 2. So therefore, you have reliability 1 and reliability 2. So that system reliability is equal to minus the of reliability each individual component. What to do is multiply. Anyway, this is just a simple superficial equation. Okay, get into details equation later. So here all we have to do is multiply dot mathematical C. Then you get it. Okay, so I'm gonna erase it. Real equation is created is the adjustment. So I'll show you. Okay. Series systems. Reliability. We have our 2, 3, A2, and it's a complex system, and they are arranged in series. Look at this expression, equation. You see the system reliability is the product of reliability each component. So component 1 is 85% reliable in mathematical value is 0.85. If you see 1, that's 100%. If you say 0.80, that's 80%, right? Okay, we have to just eliminate 0.80%. There is 1%. There's no 0 here after the decimal percent. Okay, so you can write 1 0 that is 100. Should write. So very difficult to this thing. So 100%. 0.80 is equal to 80%. Okay, so here is your decimal. So 80%. So you should be able to read decimal value into percentage. Okay, so here I have is 85% and 90%. When you write it in decimal, that's 0, 99% for 3, etc., etc., all the way, and that's the last one. Say our 4 is 80%. So when you multiply all of this, you get 0.61%. Okay, that's a system reliability. 61% system reliability. If you arrange your components in series. So if you arrange the component in series, for all system reliability is lower than each one of them. Okay, because it's longer, right? And like often. So the system reliability is about 61%. So that's a 39% chance system will not operate. Why do we get it? If the system is 100% reliable, okay, minus now it is reliable only 61%. So therefore, the system is not reliable percent, meaning it would fail 39% of the time. R is the reliability, S is your system, 1, 2, 3, all the way to N is your system component. Values are in decimal, but we usually use the term percentage, and we go 85%, 90%, 99%, 80%. And if you do and arrange them in a logical series, the system reliability is always less than reliability of each component. Okay. So 3 components with each at 0.95 reliability. I have 2, 3. When you look at the mathematical expression, my system components are arranged logically in series. So therefore, I expect, okay, my system T to be less than each component. It can never go over 95%. It's got to be less than that. So if I give you a multiple choice, you don't have to do calculation. How to decide what type of systems your components are arranged in series. So they'll try to find T for all system less than reliability for each component. Okay, it's pretty easy, huh? So some students are calculating and wasting 3, 4, 5 minutes trying to get that. All you have to do is understand that system reliability is always less than each component. I said each component. So when you look at it, it was 80%. So your overall ought to be less than that. Okay, so in multiple choice, you're going to give value less than 80% your T. Okay, teaching you that. So if you don't listen to my lecture, you're not going to get it. So anyway, so the system reliability is about 86%. That's a 14%. We take 86 out of 100, and you're going to get 100 minus 86 will give you 14% chance the system is going to fail. Right? Great. Another one, I have 4 components, 95% each. Okay. Overall is going to be lower than 95%. So you multiply 4 components reliability, you get 0.81. So the system reliability is about 81%. 100 minus 81 is equal to 19. So 19% chance system is not great. It's going to fail. Okay, not to operate means it will stop. Okay, it's not going to produce. It's not going to produce the product. All right. Okay, now we're going to increase the number of components in a series. So we did 3 components, yeah? And then we did 4 components. Look at it, the overall reliability of the system decreases. Okay, so when you take a look at this graph, this is system reliability, that's 100%, so 0%. This is a component reliability going down that way. See, going down. So you have 100 here, 99, 7, 95, 93 going down. So let's go and pick component. Okay, n is equal to 1. So right here, yeah, that means the component is only 1. This is component 2. There are 2 system reliability going down. Yeah. So here between 90 to 100. Now you have 2 components. It's now between 100 to 80. Now you have this one is a 10 components. Your reliability system is 100 all the way to 40% between. Now you have 100 components. Okay, so right here, 100 components line. So the system reliability is between 100 and 0%. And you have 50, that's between 100 0%. Here is some percentage right too. So you can see system reliability down when the components in the system increases. I want you to study this graph carefully, right? Let's get into failure rate. So failure is the absence of reliability. If you cannot rely, you fail. Yeah? You cannot rely on the system has some sort of failure right in there. So we have to fix it. So failure is the absence of reliability. So the failure rate, we write it lambda, and this is a Greek symbol. The pronunciation symbol is lambda, L-E-M-B-D-A. So it's the ratio of failures to the total item hours tested. Okay, students, they have issue to item hours tested. It's just a word. It's just the number of items you're testing. So time. So usually. So the failure rate is a ratio, meaning like ratio means it's a mathematical expression. It's a fraction. Yeah. So number of failures divided by item hours tested is a ratio. So this is you're looking at parts, okay? So you have failure divided by the number of total tested. It's a fraction, okay? Since it is a fraction, the units are the same. Number of failures, number of items, and number and number. Okay, you're looking at number over number. So let's take a look at an example how to calculate lambda, which is failure rate. Assume the 7 units of a particular product are tested for a period of 80 hours. So this is the tested hours. So hour tested 80 hours. We're not interested in hour tested, we're interested in number of item hours tested. Okay? So if 3 of the units fail after 15, 35, 60 hours respectively, calculate their rate, which is lambda. 15, 35, 60, these are the hours, okay? And those units, 3 of them, fail. So the first unit is going to fail after 15 hours. The second unit is going to fail after 35 hours. The third unit is going to fail after 60 hours, respectively. Okay? How do we know? Because we are in the predictive maintenance and management. We are calculating at what hour, which component, which item is going to fail. This is happening on paper, okay, in your program, in your computer. This is not what is happening naturally on shop floor. Okay, we are going to maintain our system, so this would never happen in real life. So calculate, we study, test, simulate, and we predict. And this is what we come up with. Okay, sometimes we do the research of using real components, let it run until they break. You will get that, okay, data when they will break. So you know exactly when they will break, plus or minus deviation. Okay, so you can protect it by replacing before they break. Okay, these are all about research. Research takes a long time, it's money, but it can save, okay, a lot in a long term, and so many people benefit from it. Okay, so calculate the failure rate, lambda. So the lambda set get the failures. So you take a look at it. Where is the failure? It's at number of failure, 3 of them. But it said it so here. If 3 of units fail, so 3 units is going to fail 3 number of failures. Yeah, divided by number of item hours tested. So we tested 3 of them. First one we tested 15 hours. The second one we tested 35 hours. And the third one we tested 60 hours. Okay? 3 of them is going to fail. The rest of them, so there are 4. The total, we have 7 units. Yeah? Only 3 are tested. Yeah? Tested. So 1, 2, 3. The total tested period is 80. 4 units, okay, is going to fail by the end of it. They weren't failing, they're still up and running. So if I have to show you visually, you have 7 units, okay, 7 units, and you're going to test period of 80 hours, okay, 80 hours. And you see the first one failed after 15 hours, okay, so, and then after 35 hours, second one failed, but you keep your system running, and after 60 hours, the third one failed. Okay? Nothing failed. Remaining 4 components running until the end of tested hour 80. Okay? These components are still running, but they will fail at the end of the 80 hours, because at the 80 hours, the finalized tested period, they all failed that. Okay? So 15, 35, 60, and the rest of them are times 80. This is the first item, second item, 2, third item. Okay? We'll count it 1, 2, 3, and the last 4 items counted 4, so altogether 7. Each one of them 15, this one, 35 tested, 60 tested hour, and 80 tested hours. Okay? Multiply that, add them up. So we get 3 divided by 30 is equal to 0.006977. So you divide 30 and you get this value. And that is the rate, okay, failure of the system with 7 points. So when you look at it, this is 100%, that's a 10, that's a 1. So you have 0.6977%. Okay? We usually use percent failure and reliability. So this is 0.6977% failure. Okay? It's the rate. Set it up. So what is the reliability? We have to use 100. Okay, minus 0.7% will give you 99.30%. There you go. Yeah. Reliability is equal to 1 minus lambda. 1 minus 0.00677 is equal to 0.993023 is equal to, change this into percentage, and you will get 0.9930. Okay, 0.9930% reliable. So change that into percentage, so you will get 99.30%. Okay. This is just a rounding. So 0.9023, cut it off here for significant figures, so I get 0.9930. Change that into percentage. The decimal 0.30 is 99.0% reliability. Okay? So you can calculate by using percentage, or you can calculate in decimal, and then at the end you can change it into percentage. Okay? So this system, since the failure rate is very small, reliability is very high. Yeah, it doesn't fail much. You can rely on the system. If your system is failing too much, then you cannot rely on the system. Okay? Their reliability and failures are complement to each other. Complement is a mathematical, it's not an English word. Okay, so I believe you know how to calculate rate. Please study this. I will ask you some questions, midterm. Okay. Last semester, about 80% gets it, 20% didn't get this, okay? Because they don't remember it, so, right? So make sure you study this until you get formula to calculate, okay? Okay, right. Number 8 is slide number 8. Some of the terms that you need in MTBF is called the mean time between failures. We usually test in our predicted maintenance, okay? Test the system, running the system to the maximum run testing period. So we usually get the mean time between the failure. So if a component is going to fail here, and another one failed there, and you have a mean time between the failures. This is a failure number. It's a failure number 2. This is a time between the two failures. Okay, the system will continue to run even if this component fails. If these components are critical, the entire system will continue to run. Okay, so MTBF check the mean time between failure is we're talking about the time between the first failure and the next one. So MTBF is the average time we expect. Okay, again, this is a predictor, so calculating everything in a program application. Okay, statistical application, mathematical application, so we can watch our system by paying attention to these times. So average time we expect to fail. Average time, okay? We expect what we think that is going to fail at this time. So we call that mean time between failure. Another scenario for the MTBF is not always like a linear, okay? It can also be the same, because your system is very complex. We can look at the components in series or in. We can also look at the same component every day, okay? So when you look at the same component every day, timeline is going with date, okay? Today it's running. Let's say today is Monday, Tuesday, okay? It's running, and after some days passed, maybe after 32 days, the system failed. Okay, here's the starting point of failure, and you repair it, and you measure again. After 20 days, we're now studying the same component. Okay, after 20 days, that component failed again. Now, so between 32 days or next 20 days, so you get the system is going to fail between 20 to 32. You can get the average of that. The system is going to fail. The average, how to get 20 plus 32. Okay, 2. So you can get like 20. Okay, 20 plus, okay, here's my calculator, 32 divided 2 will give you 26. Okay, average time. So this 26, okay, average time, 26 hours is going to be MTBF. Okay, if you study the same but days in between. Okay, I just gave you 2 scenarios. One is a in series, and if they fail one by one, so call the MTBF. If you study the same comp, if they fail some days apart, some hours apart, it's also MTBF. So you know that MTBF time, okay, it can be second, minute, hour, days, weeks, year. Okay, so all the time unit, pay attention to that. Don't just remember MTBF is in hour. It's not like that, okay? But commonly in hour because we're dealing with the operation hours, okay? Alright, availability is a time. Again, another time factor. So I'm just write time, and here is a time. So the time we expect the equipment to be operational. Since it is operational, it is available to do the work. Okay, so availability, time, we expect the equipment to be functioning, to be operational. Mean downtime, another time. And that's the MDT, okay, mean downtime. M and D, T. So it's mean time between failures. So average total time it takes to return failed back to operation after fixing it. Okay? So since your equipment is failed, you can use it, so therefore all that downtime of that equipment can be a machine or it can be a tool, whatever. Usually is a machine in the manufacturing environment. Okay, so mean downtime, you can use that equipment or the machine. So you gotta repair it back to operation. You measure the time from the time it failed, okay, to the time that you can run it again. The downtime, it can be again, second time, days, weeks, and year. Okay, it's all big system. You have to know how to calculate mean time between failure in industrial maintenance. So you are managing how to do it and will be able to manage that system. So you need to know how to calculate the mean time between failures. Very critical. So mean time between failure is the reciprocal of failure rate. Reciprocal. Okay? Another mathematical term. So make sure you have MTBF is equal to 1 divided by failure rate. Failure rate is like this. You always have a hidden fraction divided by 1. So everything, if you have 2 in number, that means that 2 divided by 1. This part is hidden in mathematical expression. It's called a silent, silent values down there. Like you have silent letters or alphabets in English pronunciation like that. So mathematical, there are silent parts. So if you see a whole number 1, there is a 1 down there. See a whole 13, there is a 1 down there. They can always be written or expressed in fraction. Okay. So when you see a symbol, the same thing. Symbol is a representation of a value. So lambda can be any kind of value. Every value has a hidden fraction expression, which is divided by 1. So now the reciprocal of the failure rate. Lambda is a failure rate. Reciprocal of it is you take it upside down. You put this up, put this down, okay, in the fraction. So you get 1 divided by the, it should be so 1 divided by lambda. And this is your MTBF. That's how you calculate MTBF. Okay? So if I give you lambda, you should be able to calculate MTBF. Okay? And if I gave you MTBF, you should be able to get lambda. Okay? By using this relationship. MTBF is a reciprocal of failure rate, and the failure rate is a reciprocal of MTBF. And that's just your algebra. MT. I hate this thing to write. Okay, so now let's take a look at the little example previous. So we have a failure rate of 0.7%. So if I ask you that and find mean time between failure, you're going to get a reciprocal and get 0.0 divided by 1 reciprocated, so 1.0007 is equal to 140 hours. Okay. All right. Availability time again. We're going to calculate by using this formula. Use a mean time between failure, the mean time between failure plus mean downtime. How to get this one by heart? It will be in your midterm. Okay. I told you, if you're not listening to the lecture, you wouldn't know. Okay. So here, improving system reliability. Improve the system design. Again, if you improve the system design, you can improve system reliability. We already know if you arrange the components of the system in series, the system reliability will go down. So if you want to improve the system reliability, you want to reduce that series. Yeah, so you will go up. So use a backup and add redundancy. Okay, and use a backup. But since we're not studying the system engineering, so we don't get into detail of that. So if you know this theoretically, you're okay. Parallel system. So let's get into parallel system reliability calculation. System reliability, our component is in parallel because I, C, you're taking it off from 1. Okay? So every time you see you're taking it off from, then multiplying right here to here, so I have 3 components. Yeah? Component 1, 2, all the way to component N. So right here we have only, in this example, we have only 2 components, right? Component 1, component 2, component 1 is at 80%, 85%, sorry, component 2 is at 90% reliability. And we're going to calculate each one. So you get the overall reliability system range in parallel. Okay, so you're going to get RP. This is a system failure arranged in parallel. So we already knew how to calculate the overall system reliability in parallel arrangement. So it said it's a when component system are arranged in parallel, system reliability is 1 minus product of reliability of each individual component. Okay, so here is a product, and this is the reliability of each component. And students usually forget, right? The formula has 1 minus 0.85 in it. Okay, and they usually, it's very confusing for some of them, but then don't forget that the formula is 1 minus R1. Okay, 1 minus R2, and then multiply. Okay, and then take it out for 1. So what they cannot understand is they're looking at 1 minus R1. Okay, it's actually failure, because the failure and reliability, if they add together, you get 1. Okay, so now the reliability of the one is 0.85. Yeah, so 1 minus 0.85 give you failure. This is failure. You multiply the failure of each comp, take it off of 1. Okay, if you minus the total failure, you will get the reliability of that system. Okay, So that's why don't forget that there is a 1 minus r in it. Okay? In the very first slide, I show you superficially like this. Okay? We're going to multiply ability of each component and take it out from 1. Okay? That's just to support how we write in English about it. Okay? But for mathematically, you have to understand the arrangement of that system. Okay? In English, it's easy to say it, but when you write it down in a mathematical expression, it's a different thing. So in English, we say when components of a system arranged in parallel. Okay? So mathematical expression is different because of this word, arranged in parallel. It's automatically understood this way. So in English, where we just write the system reliability is 1 minus product of reliability of each individual component. Okay? And that's a common word that we use, okay, in language, which is not precise in equation. So they should actually change this into failure. Order of the failure of each individual component and get rid of, okay, when the components of the system are arranged in parallel thing. So all you have to do is system reliability, okay, in parallel system is 1 minus of the failure of each individual component. And that's what I found weakness of the language that we use in this textbook. Okay, because it makes you understand, in a deviated way. I cannot change the author's original word. Okay, that's against the rule, compliance. But we don't change the intellectual property of another individual. But I can point that out. Think, if you read it in this way and don't know what to do, they are arranged in parallel and don't know how to write adequately. Okay, for this arrangement, you're going to have an issue. Okay? You cannot put it on the author language issue because he is right. Because he is writing this way when components of the system are arranged. And so it is your own failure, okay, who can't understand the math. Okay, so if I read this, also it depends on the experience, okay. I understand that this system is parallel. Therefore, in order for you to get, okay, the system reliability, you have to consider this failure at that point. Multiply that and take it out from 1, you will get the reliability, okay, of that parallel system. For series is pretty easy. So they're going this way, arrangement is, okay. So all you have to multiply that. Don't need to find the failure of any of that. Okay. So why do we have to calculate the failure this way? It's because of this branch. Okay, because of that. And you wouldn't be able to understand it right now, but you get it. But it's a fine, a tickling to think of it. But anyways, I point that out, so forget it. Okay? I would just go bracket like this. Yeah. And some people don't want to write bracket, but this is the correct way. This represents actually failure. 1 minus 0.85 is a failure at that component. Failure 1, failure 2. So failure at component 1, failure at component 2. Okay, multiply that, take it out from 1, would give you the over thing. Okay, I think got it. So about 80% of the students get it, because only 80% listen to my lecture. 20% they don't, they only read the handout. Okay, when you read the handout, you're not getting what the professor trying to show you of the things that you can miss by reading, okay, textbook without understanding mathematics and also the structures, the arrangement behind it. Okay, these are mechanics. Mechanics doesn't go with English. Okay, this is a natural phenomenon that is happening in the nature. Okay, science is discovered this nature, these things in the environment, okay, that cannot be described precisely by using a language that can only be studied, discovered, and repeated. Okay, so make sure you don't skip lecture, you don't skip class in order to be able to get these things. Okay, let's go to the next one. So now we're going to combine the series and the parallel systems. Okay, so here I have parallel, and this parallel and that parallel and this little component are in series. Okay, so first we're going to study this part. That's a parallel part in your first system. So let's get this reliability of that first part, which is parallel. So the parallel system, to get the reliability of this first part, it said it so. Please get the failure of each component. So we're getting the failure of each component by taking the reliability out of one. Okay? And minus that product. This is a product from 1. Okay, so 1 minus the failure is going to give you reliability. So I get 0.625. Okay, so here I got 0.96. Okay, if you round it, here is on 96%. Now we're going to do the same thing for the second part. Okay, second, there's your first part, your second part. So the second part has a 3 components in parallel. We do the same thing, get failure at each component by taking the reliability out of, multiply them. Okay, this multiply that, and take it off from 1, and you reliability of this arrangement, just in parallel. So that's 99%. So that's a 0.99 right here. Okay, and then the third one is just a single component, so therefore that's 0.90. Okay, so now I have a series just going straight just like that, so therefore overall got to be lower than 0.0. Yeah? So you do multiply all that, 3 reliability, 0.96, 0.99, and then 0.0. So you will get 0.86, which is less than the smallest reliability, okay, of a part in the system. So you get 0.8600, 0.86. So that's 86% reliability, okay, for this first, second, third system. Now I want you to study this, and similar problem be given to you in midterm. Okay, midterm I think is going to come February something, February 19th. So make sure you how to calculate that. Logical meaning components are arranged in a logical manner, either in series or complex parallel, and complex parallel series arrangement. Okay, so if I give you a non-logical system, you should be able to come up with a field system as well. Okay, in order for you to get value of probability of the system, your system arrangement got to be logical. So if I give you some nonsense system, you will get no reliability. Okay? So, okay, well, yeah, this is the end of this chapter. So to conclude this chapter, make sure you understand failure, system, reliability. You understand the logical arrangement of system components in that system and the overall reliability, how to calculate them. Try to understand testing that we do. Try to understand the rate, failure rate lambda. Try to understand the reciprocal of failure rate, which is your mean, MTBF, mean time between. Try to understand the T and the mean downtime. Okay, how to calculate all of that. Right, so in this chapter.